Welcome to the deep dive, everybody. Ready to tackle a huge topic. Abstraction, it's everywhere, but how does it really work? Especially when things get super complex and, uncertain, like trying to predict the stock market or getting a handle on climate change. We're diving deep today, and our guide is this paper, An Algebraic Framework for Hierarchical Probabilistic Abstraction by Upridi and Bell. It's a bit dense, but we'll unpack those brainy ideas and make sure they actually make sense.
Absolutely. It's all about finding a structured approach to
Yeah.
simplify these complex probabilistic models without, losing the heart of what's really going on.
Okay, so let's get into it. Abstraction. What are we even talking about here?
It's a bit like making a simpler map of some really complex terrain. Imagine a massive data set, thousands of variables. Abstraction helps us shift from that very granular level to something a bit more manageable. But, and this is key, while still capturing those crucial probabilistic relationships.
So it's not about ditching information, but about finding like a more efficient way to represent it.
Exactly. Think about different maps you use, right? A road map is great for driving, but then, a subway map is more helpful if you're navigating a complex train system. Each level of that abstraction, it serves a different purpose.
Gotcha. And the paper outlines three foundational types of abstraction: direct, divergent, and convergent. Let's break those down. What's the deal with direct abstraction?
So that's your simplest type, like a one-to-one mapping. Each element in our complex system has a corresponding simplified element in the abstract model. Like if you were summarizing a really long paragraph into a single concise sentence.
So finding like the essence of each element.
Precisely.
What about divergent abstraction?
Now things get more interesting. One concrete element can map to multiple abstract elements. Imagine a doctor diagnosing a patient, right?
Yeah.
One single symptom could point to several different conditions. It's a one-to-many relationship.
So we're branching out in the abstract model, exploring all these possibilities from a single starting point. Okay. Then how does convergent abstraction fit in?
Convergent abstraction takes us the other way. So multiple concrete elements are combined into one abstract element. Think about how market researchers group individual customer behaviors into broader segments, many to one, right? Simplifying a bunch of data into these more manageable categories.
It sounds like these three types are like tools in a toolkit for building different models, depending on, how complex things are.
Exactly. And this leads us to hierarchical probabilistic abstraction models, or HPMs for short. These models, they let us combine these building blocks in some really powerful ways.
So we're going beyond simple maps to like building a multi-layered 3D model.
That's a great way to put it. The paper focuses on HPM DAGs, where DAG stands for Directed Acyclic Graph. We're creating essentially a hierarchical tree-like structure. Think of a family tree, right? You've got the detailed information at the bottom, and then as you go up, you reach more abstract, higher-level concepts.
Okay, I'm starting to see how this hierarchical view could be so useful for really getting a handle on complex systems. No more getting lost in like confusing loops or circular relationships.
Exactly. The authors give a really good example using a personalized learning system for students. They imagine a system that considers all sorts of factors influencing a student's learning. Everything from, their home learning environment and their cognitive abilities to their socioeconomic background.
Wow, that's a lot of variables. I can already see why a single layer abstraction wouldn't cut it in a case like that.
Right. A hierarchical approach using HPM DAG lets you build a much more nuanced understanding. At the lower levels, we can capture these really specific relationships, like how, let's say, access to technology might impact a child's problem-solving skills.
Okay, so we're like digging into the details at the base of the tree. What happens as we climb to those higher branches?
As we go up, we get a more holistic view. We start looking at things like overall student engagement, motivation, and then ultimately academic performance. It's about connecting the dots, from those granular details to the outcomes that we care about.
It's like having that zoom lens. We can adjust our focus to see the individual trees, but also the whole forest. But that raises a crucial question. How abstract can we go before, we lose too much valuable information?
And that is where the concept of the highest possible abstraction comes in, or HPOA.
GPUA. Okay, tell me more. Sounds like finding that sweet spot between being simple and being accurate.
It is. It's the most abstract level you can achieve while still making sure your model, the simplified one, accurately reflects the probabilities of the original, more complex system.
So it's about maximizing efficiency, but not at the expense of, like, the model's predictive power.
Right, making sure our abstractions stay grounded in the probabilistic realities of the system we're studying.
Wow, this is fascinating stuff. So we've got the building blocks, we've learned how they can be combined into these powerful HPM DAGs, and we've even touched on the HPOA. Where do we go from here?
Well, the paper dives into even more complex scenarios. Remember those three basic abstraction types? They can be combined in even more powerful ways. Which brings us to the idea of hybrid HPMs.
Hybrid HPMs. Okay, now it sounds like we're like in expert territory here. What makes these hybrid models so special?
Hybrid HPMs, they give us a lot more flexibility, more power. We can combine those abstractions, the sequential, the divergent, and convergent all together. And that really helps us mirror how complex the real world is.
Can you give me an example of how that might work?
Absolutely. The paper, it uses Alzheimer's disease to kind of show off the potential.
Alzheimer's, yeah, that's definitely a huge challenge. So many factors, all intertwine. How could a hybrid HPM help us untangle all that?
Okay, so imagine building this model in layers. The base level, that represents the different risk factors for Alzheimer's
Oh.
in a population, right?
Hmm.
Things like age, genetic predispositions, lifestyle choices, even, environmental factors.
So we're starting broad, looking at the whole picture of risk. What's next?
Then we use sequential abstraction to shift to a layer focused on the biological side, the mechanisms of the disease. Think about the buildup of amyloid plaques, the tau tangles, or any other biomarker we can measure.
Okay, so we're getting more specific now. From those risk factors to what's happening in the brain, where's the hybrid part come in?
From that biological layer, we can branch out using divergent abstraction. So one path, let's say, represents those patients who are receiving drug therapy. Another path models the ones doing cognitive stimulation therapy.
Ah, so the model like splits to let us see how different interventions compare, almost like running different simulations at the same time.
Exactly. We can model how each path impacts those biological markers we talked about, and ultimately how it influences a patient's cognitive function over time.
Mhm.
And then convergent extraction comes in to bring all those separate paths back together.
So we're not just exploring them in isolation. We're seeing how they all like connect back to the overall effectiveness of treatment. What kind of insights could this model give us?
Imagine taking an individual patient's data, all those unique factors, the genetics, the current markers, and then using the model to simulate how they might respond to different treatments. That could be huge for personalized medicine. Doctors would have this tool to really tailor treatment plans.
It's like having a crystal ball to peek into the future of a patient's health
Mhm.
and make better decisions.
It's not just about personalized medicine either. These models, they could help shape healthcare policy. We can figure out which interventions work best for different groups of people. We can use resources more effectively
Hmm.
and even design, more targeted prevention strategies.
We're talking about changing the whole game for Alzheimer's research, treatment, prevention, everything.
This kind of modeling, it has the potential to transform how we understand these complex diseases,
Mm.
lead to a more data-driven approach to healthcare and a more personalized one.
It seems like HPMs are this robust framework, right? That we could apply to tons of problems. What other areas could we use these models in?
Oh, the possibilities are huge.
Right.
Financial markets, managing the environment, understanding social dynamics, even designing AI, a more sophisticated kind of AI.
Mhm.
HPMs could change the way we think about complex systems in just about any field.
Okay, so we've explored abstraction, right? We've dug into the nuts and bolts of these hierarchical models, and we've even seen how they might change healthcare and other fields. What's the key message our listeners should take away from all this?
Yeah, it's like we've got this new way of thinking now, a way to approach anything that's complicated and uncertain, from those basic building blocks all the way to like those sophisticated HPMs. And we saw how they can apply to everything from kids learning to Alzheimer's.
And it's even more fascinating when you realize that this research, it has these implications that go way beyond specific applications. Abstraction, it's not just something we use to make models, it's how our brains work, right? We're always abstracting information to make sense of the world. We
Yeah.
form these categories, we make predictions, we learn from experience.
So by studying HPMs, we're also like getting a peek into how we think. Yeah, that's what's so cool about this.
Huh.
If we can figure out how these hierarchical models work, could it help us design AI that's more human-like? Systems that reason with probabilities, that adapt to new information, maybe even, show some creativity.
It's like we're not just modeling the world anymore. We're kind of reverse engineering, like the whole process of understanding.
Exactly. And that leads to some pretty profound questions. If we can create AI that thinks more like us, what does that mean for the future of, work,
Hmm.
education, even our understanding of consciousness?
Those are definitely some big questions to think about. But for now, let's bring it back to our deep dive. We've covered a lot of ground, explored the power of abstraction and how it can be used in so many different areas. What would you say is the most important thing for our listeners to take away from this?
I think the key takeaway is simply this. Abstraction, it's a powerful tool for navigating this complex world that we live in. And by understanding the different types of abstraction and how they can be combined into these hierarchical models, we can gain deeper insights into any system. We can make better decisions, and we can even start to unlock those secrets of how we think, how the human mind works.
Well said. And as this field keeps evolving, who knows what other amazing discoveries are waiting for us. I'm already looking forward to our next deep dive into, the world of these complex systems. Thanks for joining us, everybody. And until next time, keep exploring, keep asking those questions, and keep abstracting.